Okay, welcome to Note Set 8, where we'll be talking about the concept of elimination, which is a formal way of solving a set of or a system of linear equations. So we've kind of alluded to how to do this in the previous set of notes, and this will take you through kind of like I said, a formalized way of doing that. And in doing so, we'll see more insight into the mechanism by which all these equations work, and when we have solutions and when we don't have solutions, when the solution is unique and when we have infinitely many solutions. And this material is coming out of section 2.2 of the textbook. So here's what we're trying to solve in our matrix format. AX equal to B, and generally when we talk about solving this system of linear equations like this, we imagine that we are given the coefficient matrix A. So A holds all the numbers that are the coefficients in front of the variables. X holds the spots of the variables, the things that we don't know. So and then B is a vector that holds some known numbers that are, the linear combination of the different variables are equal to those values. And you'll note here that we have indicated that we often think of vector B as the output vector and X as the input vector. So we can, in some scenarios, we can think of X as being something that goes into the matrix, and B is the thing that comes out of that operation of multiplying A times X. And this keeps coming up here. Keep the current color scheme. Okay, sorry about that. We think of X as going in, being operated on A, and B is what comes out. And so we can think of A as representing some sort of system, X is some sort of input to that system, and B the output. And what we have is we know the system, A, we know the output that arises, B, and we're trying to figure out what went into the system to create that B. So in many engineering applications, that's a very important way to view these kinds of things. In a circuits problem, A characterizes the structure of the circuit, B characterizes some known or measured voltages, and X is the some unknowns that we're trying to solve for. So we'll take a look at this example here where we're trying to solve for X and Y. Now, sometimes we will think of the elements of X as being like X1, X2, X3, and so on. That's convenient when there are many elements. But if we're talking about systems where we have just 2 or 3, we'll call the elements of X and Y, or the elements of the vector X, just X, Y, and perhaps Z if we have 3 elements. So this X and Y here are the elements, the unknown elements of the vector X. So here, excuse me, here's the 2 equations that we want to solve. We call this a system of linear equations, and this is a set of 2 equations for which you can't just look at it and go, oh, I see the solution. So that we say the solution is not obvious. And so how are we going to solve that? And so one method that we use is this idea of elimination. So if we can eliminate one of the unknowns in one equation, then we can solve that one equation for that for the value of that one unknown. So here's step 1. We write down the given equations, and what we're going to do is multiply the first equation by 3. So we're going to take this equation here multiply both sides by 3, so we'll get a 3 times x, a 3 times a negative 2, and a 3 times a 1. And so when we do that, we get our 3x minus 6y is equal to 3. So all we've done is we've done a modification of the first equation, but notice that multiplying both sides does not change the fundamental nature of that equation. It will still be solved by the same set of x and y. So we haven't really changed anything by doing that. So that's the first step. And then step 2, we've rewritten that, and the step becomes subtract it from equation 2. So we're going to take this, and we're going to subtract it from this equation, the second equation. And you can see that we're going to be taking a 3x and subtracting it from 3x. And so that will actually cancel. And so that's how we're eliminating one of our unknowns. Once we do that, we'll get a new equation that will most likely depend on only y. I say most likely because there is a possibility that we could also cancel the y term, and we'll look at that situation later on in this set of notes. Let me clear off some of this ink here. So the real question is when we get this equation. So there it is. So we are going to subtract 3x plus 2y, that's this part, minus 3x minus 6y, that's this part, on one side, and then on the other side we're going to have 11 minus 3. And when we do that, if we notice that the x's cancel, we're left with 8y is equal to 8. And now at this point we have to say, what have we done here? Is this an allowable step? Why are we allowed to subtract this multiple of equation 1 from equation 2? Well, it's a little difficult to see it now, but in subsequent note sets, we'll be able to actually establish. We won't go into a formal proof of it, but we'll see why this is a viable step in that we get a new equation that we can couple with the first equation and have a new system that is completely equivalent to the first system. So what we're going to do is we're going to take this new equation, which is now 8y is equal to 8, together with the first equation. And our claim is that those two equations together will have the same solution as the original two equations together. And we've not proved that at all here, but it kind of makes sense. I'm sorry for the coughing here, but suddenly I have something stuck in my throat, I think. And so the purpose of having done this is we've eliminated the x. So we eliminate one of the unknowns. So this new equation has only y in it, and it's very easy to solve this. We divide each side by 8, and we end up with y is equal to 1. And so y is equal to 1 is part of the solution to the original system of equations. And so now we substitute that solution back into equation 1. And so this step is called back substitution. So the first step is eliminating the variable, one of the variables, in this case x, and then we back substitute it into equation 1 and solve for that. So once we substitute y equal to 1 into the first equation, we get 2 times 1. So this equation now becomes x minus 2 is equal to 1. And that's what we have here. And so that's an equation just in x. Very easy to solve for that. We take the negative 2 and we move it over here to the other side, and we get x is equal to 1 plus 2, or x is equal to 3. So we now have solved this system of equations through a fairly formulaic, systematic approach called elimination. Now there's a few gotchas here and there that we have to deal with, and we'll take care of those towards the end of this note set. But that's the basic idea. So let's summarize what we did here. And so we can see that at the top on the left, we've got the original set of equations, and then I've just written them below that in the matrix form. So you can see that we have the coefficients. We've got the 1 and the -2 and the 3 and the 2 all form this matrix A. Then we've got our unknown vector x and y, and then we've got our B vector, which comes from the 1 and the 11. And so let's look at what happens when we multiply equation 1 by 3 and then subtract that resulting multiplied equation from equation 2. And when we do that, we now have these two. And if we put that, and this is called the process of elimination. And if we put that into a matrix form, we can see that the matrix now has a structure which we call upper triangular form. So if we look at the diagonal of the matrix, there are numbers on the diagonal, and there are numbers above the diagonal. Well, technically there is a number below the diagonal, but it's 0, and that's the point. So for upper triangular, every number below the diagonal has to be 0 in order to be upper triangular. Now, there's only 1 below the diagonal for a 2 by 2, but when we go to 3 by 3 or 4 by 4, there will be more numbers down there. And so everything below the diagonal has to be 0 in order for it to be upper triangular. And so nothing happens to this, but this does get changed. It changes. It was 1 and 11, and now it's 1 and 8. But the key is that we've created an upper triangular form. Let me clear this stuff off here. Come on. So once we get it in upper triangular form, we notice that the bottom equation ends up being just an equation in one variable, and we can solve that and for y in this case, and back substitute it in to solve. So once we know that y is equal to 1, so this little arrow here, this little arrow here is just showing back substituting. So we substitute y equal to 1 back into the first equation, and we end up with a solution. So we've got elimination followed by back substitution, allows us to solve the system. So in a previous set of notes, we talked about the row picture, imagining each equation in 2 dimensions anyway, defining a line in the 2-dimensional space. So here we have our 2 equations. Let's think about what those things look like. Now, we can see the 2 equations here. So this one is due to the first equation, and this line is due to the second equation. Now, I just want to point out in passing that anything that looks like this is an equation for a line. Now, you may be used to seeing it in a different form, so you may be used to seeing y is equal to mx plus b, and you can convert each of these into that form. So if we take this -2 and move it over to the other side, take the 1 and move it over to here, just doing simple algebra, and then divide both sides of our equation, we will get something. We will isolate y, and whatever the number is that's in front of x, that's the slope of that, and whatever number we end up with out here, that's the y-intercept. And so you can see that the slope of this line is 1/2, and that comes from the x having a 1 in front of it being divided by the 2 to give us the 1/2 when we isolate y. And likewise, you can see that this has a slope that's different from that. And you can figure out what that is. It would be -3/2. And you can also figure out what their intercepts are. So I just point that out as we pass through here, because you may be, it may have been a while since you've seen this idea of an equation of a line, and also, the form that we're working with here is not the most classic form for an equation. But the bottom line is, if you've got two variables, x and y, and all you've got is some coefficients in front of them, adding together with those coefficients applied is equal to a constant, that defines a line. So there's the two lines, and where they intersect, that's the solution. That's what we mean by solving this. So the first equation just says, well, every x and y on this line solves that first equation. And the second equation says every x and y pair on that line solves that. But there's only one place where there's an x and y that solves both of them, and that's the solution to the system. So let's see what happens when we, after we do our elimination. So after we do our elimination, we get this set of equations, and we haven't proved this, but we're at least alluding to the fact that this is valid, that this set of equations should have the same exact solution. And if we look at this, this bottom one, well, it's saying y is equal to 1. Remember, what we really came up with was 8y is equal to 8. So that's why they have this version of that equation there, which is equivalent to y is equal to 1. So that goes through the y-axis at the point y is equal to 1. And so y is equal to 1 is saying that there's no dependence on x. So for each value of x, the y value takes on the value of, or the y variable takes on the value of 1. So that's what makes it easy to solve, the fact that it's a horizontal line. Now, if we had eliminated y, which we could do, and I would encourage you to try to eliminate y instead of eliminating x, you'll actually get a lower triangular system then. Works just as well. What you then get is a vertical line that would go through here, and you would retain the second equation, which would be this line. So those would be the two lines that you would have, and despite my poor drawing, they would actually intersect at the same place. So when you isolate one of the variables in this two variable system, you'll get either a horizontal line, as we actually showed here, or a vertical line, as we just alluded to. But the important point is that the intersection point, the solution, is not changed after elimination. Now, in a math-oriented linear algebra class, we'd have to prove that. And like I said, in subsequent note sets, we'll see some results that will make it a little clearer why this is true. But we're never going to do a formal proof of this. So, what was the rule that we used to transform this? We want to come up with a nice systematic, formalized way to do this. In fact, we want it to be so formalized that we could actually write some computer program code to do this for us. Because if we're trying to solve a system with hundreds of variables in it, which might show up in a very complicated engineering problem, we don't want to be doing this by hand. But we should be able to put this into a computer with the appropriate program and have it solve it. So there needs to be some sort of systematic way. Now, you might be saying, all right, fine, I'm sure somebody has done this already. Why do I need to know? Well, as I've already tried to convey to you, knowing that there is a tool and I can use it is generally not the only thing you need to know to be a good engineer. To really understand how the tools work allows you to be a clever engineer and come up with better ways to do things. So the elimination part we saw gets rid of x in equation 2. And what we did really was to subtract a multiple of equation 1 from equation 2 to get a new equation that has x eliminated. So here's what we're going to do. Subtract a multiple of equation 1 from equation 2. And in this example, we needed to multiply the first equation by 3. And so the question is, where does that knowledge come from? How did we know to multiply by 3 and then subtract it from equation 2? So let's look at that more systematically. So if we think about our first equation, we've just put a 1 in front of the x so that we can see the coefficient out there explicitly. And there's our second equation. And so what we need to look at are these coefficients. And there will be some names for this, at least a name for the one in the equation that we're using to do the elimination. And so the name that we use for that is the pivot, or a pivot. So so we're looking at the equation here, the first equation, and we look for the coefficient in front of the variable that we're trying to cancel. In this case, it's x. And then we look at the coefficient in the second equation for that same variable, and in this case it's 3. And it's pretty clear that after multiplication we need to make those things equal to each other, so it's pretty clear that we multiply the first equation by 3. But let's look at this in another case where the pivot isn't equal to 1. So now it's pretty clear that if we multiply equation 1 by 3/4, so we'll be taking this 4 times 3/4 will give us 3, because the 4, which we'll have out here, will cancel with the 4 and we're left with 3. And so that'll give us a 3 out in front that we can then subtract from the second equation to eliminate the x variable. And so we would get something that looks like that. In this example, the last equation still ends up giving us y is equal to 1. And back substitution produces x equal to 3. But so what's more important than just being able to solve this particular example is to kind of see the mechanism by which we do it. So the pivot, again, we define to be the coefficient on the first row that is the first non-zero coefficient. So in our case, that's putting the variables or the terms in order. We've got x and y. So we've got 4x, so 4 is going to be the pivot for this step. So the top row's pivot is 4, and then the coefficient is going to be the corresponding number in the equation where the elimination is going to occur. So we're trying to eliminate x in that second equation. So 3 is the coefficient. So the bottom row's coefficient is 3. And then to find the correct multiplier, we take the coefficient that we found, which is 3, divided by the pivot that we found, which is 4. And that gives us the 3/4 that we specified as our multiplier. And so 3/4 is the value in this example for the multiplier. And then you can see that when we multiply the top equation by 3/4 and subtract it from the bottom equation, we end up eliminating x and getting 8y is equal to 8. Okay, so here's a couple exercises. I would encourage you to stop the video now, give them a shot, and then come back, restart the video, and you can check your solutions. Okay, hopefully you paused it, went through the examples or the exercises, and have your solutions. So let's take a look at how these work. Now you may have come up with a okay, so if you did go through these exercises, you may have found that you ran into some problems. So let's take you through these and see how you deal with these problems. So failure is possible when we try to do these things. So let's go through these elimination procedures and see what happens. So here's our equations. X minus 2y is equal to 1, and 3x minus 6y is equal to 11. And so we're going to use our standard approach here. We're going to say we've got a pivot of 1. We've got a first coefficient of 3, so we take the coefficient divided by the pivot, and that's the multiplier. So our multiplier is 3. And when we do that, we get something that looks like this. So not only did we eliminate x, but we eliminated y. And so now what number, y, can I multiply by 0 to get 8? And the answer is there is no number. And so, if we think about it, we can think of this as a pivot for the new equation. And we can never allow a pivot to be equal to 0 because we end up having to divide by pivots in our procedure here. But more importantly, when we end up with a 0 pivot on the last equation, it tells us that we can't get a solution. So keep your eye out for pivots that are 0. It will be a key to tell you that something is up with the equation. There's some issue that needs to be addressed. So let's look at this no solution failure from the row picture scenario. So for problem number 1, we said that our first step in elimination is to multiply by 3 and then subtract that equation from 2. We get something that looks like this. And so why did this happen? Let's see if we can get an idea. So we get some insight to this from the row picture. So if we take these two equations and we plot them, we get two lines that are parallel. And I've just done a little conversion into the standard y is equal to mx plus b form. So we've got y and x. So we want to solve it in y is equal to some function of x form. So if we just solve this equation for y, we get something that looks like that. And we see that we have a slope of 1/2. Same thing, we take our equation 3x minus 6y is equal to 11. We solve that for y, and we get 1/2 x minus 11, 6. And you can see that they both have the same slope, right? This one's got a slope of 1/2. This one has a slope of 1/2. And when lines have the same slope, we know that they are parallel. Now, they are not the same line because they have different intercepts. So we see that this one has an intercept of minus 1/2, so it's going there right between 0 and -1. And so -2 is down here, and -11, 6 is just shy of -2. So that's why there's no solution. Parallel lines don't ever intersect, and so there is no solution. And so when we get a scenario where we have a 0 pivot, but there's a non-zero value over here, that's an indicator that there's a problem, that there is no solution. So mathematically, or equation-wise, we see that in the upper right-hand corner, and from a graphical math point of view, we see why there is no solution. So the other thing that we can see is that when we have two equations like this that have the same slope, when we write them back into this, y is equal to mx plus b form, that comes from the fact that if we look at the ratio here, 1 to 3 versus 2 to 6, that's the same ratio. And that's what gives rise to there being the same slope. Because to find the slope of this first equation, we would have to divide by the 2. Well, we'd swing it over to the other side, which is why we would divide by 2 and not negative 2. So we would have 1 divided by 2, and over here we would have 3 divided by 6. Both of those give us that 1/2 slope. And so that's why the same slope gives us the same ratio on the coefficients within each equation. And so look at what that does, right? When I have the same ratio between 1 and 2 and 3 and 6, when I multiply to make this so that it cancels this, this will also be made to cancel that. And so that's why we end up canceling both, and we get a 0y is equal to 8. So that's the problem. So that's looking at it from the row picture. Let's look at what's happening from the column picture. So this is looking at the no solution failure from the column picture. So there's our equations, and there's after elimination. And so now let's look at this situation here. We have two columns, 1, 3, and -2, -6. And if we put those out onto our plot, we see that they lie on the same line. So that's the first issue. And then the second thing is that there's no way to combine those to give the given B. So all the combinations of the columns lie along the same line, but the target output, the given B, is off from that line. So the only thing we can compute or create by linear combinations of the two columns are things that lie on that line. It goes through the origin, and both of the columns lie on them. So if B happened to lie on that line, then we would have not only a solution, but infinitely many solutions, as we'll see in just a little bit. So now we're looking at that same thing, that it's kind of the same ratio issue again. We've got 1 to 3. That tells us kind of the how this vector is sloped, and -2, -6 tells us how this other vector is sloped. Well, they have the same ratio. 1 to 3 is the same as -2 to -6. And so that's why they lie on the same line. So we're seeing essentially the same kind of thing here. Okay, so now you should be able to identify, at least for these two-dimensional cases, but you should be easily able to extrapolate to 3 dimensions and higher. But we've got an inkling now as to how does failure happen in elimination, and how does it get linked to a situation where there's no solution. But now let's look at problem number 2, and we'll see an issue with infinite solutions, and how infinite solutions also leads to a failure of elimination. And first we'll look at this from the row picture. So we've eliminated, so we find our pivot is 1. The other coefficient is 3, so the coefficient divided by the pivot is 3, and that's our multiplier. Subtract it from equation 2 and we get something that looks like this over here. And now we see, hey, yes, we have eliminated y as well, but it's different than in the previous example, right? Let's back up a little bit. There we had 0y is equal to 8, and so in that case there is no y value that works. But what about over here in this new scenario? 0y is equal to 0. Now any y value works. So there are infinitely many values of y. You give me any value of y and it solves that equation. So every y satisfies this 0y is equal to 0. And basically we've completely eliminated that second equation. There is no second equation. And so there's only one equation left. X minus 2y is equal to 1. And so we can pick any y to solve our system of equations. And when that's possible, we say that the unknown variable y is said to be free. We're free to choose anything we want. And then once we choose a specific y value, then we can figure out which x value corresponds to that selected y value. But there's nothing constraining us from picking certain y values. We can pick anything we want. But x is not completely free because x must be chosen so that whatever y you pick and put here will determine the corresponding x. And so in this case, we see the two equations written here, and you go, hey, wait a minute, I see only one line drawn. Well, that's because these are the same line, right? If we put each of these in the y is equal to mx plus b form, we'll see that they are exactly the same line. So we have two equations that are basically just one equation. And that's why up here, after elimination, we've eliminated one entire equation, because there really aren't two different equations. There's only one. And so that's the row picture. Let's take a look at the same problem from the column picture. So our multiplier is 3. We end up getting something that looks like that. But now let's look at this from the row picture, more over on the left, the top left, that stuff. So if we look at that, our target output B is now the same as column 1. So our column 1 is 1, 3, as is B. Now, it doesn't have to be equal to one or the other of the columns. B can be equal to anything that lies on the line in which those two columns fall. So, the left side of this problem is the same as problem number 1. So we've already seen that the two columns in this case lie on a single line. But unlike in the first problem where B was not on the line defined by those two columns, in the second problem the B that we're asked to deal with is. And so there are infinitely many ways that we can create this given B. So one thing we can do is a solution of 1, 0. So if you think about what that means taking 1 times the first column. So the first column is 1, 3, and we have 0 times the second column, plus 0 times the second column. So that will solve it. But we could also take 0 times the first column and negative 1/2 times the second column. So this is showing 1/2 times the second column. So negative 1/2 would just flip that over and we would take it right out to the point. And there's other ones. I would encourage you to play around to try to figure out how you would create this. So I'll give you one here that I can figure out off the top of my head. We could take half of the first column minus a quarter of the second column, that also would be a solution. But try that out. Try to come up with other solutions. You can always then plug them back into the equation to see if they do indeed satisfy. So in conclusion, for this first part of this set of notes, we can have scenarios where the elimination can go wrong. And I apologize for giving you those as exercises and asking you to work on them, only to tell you that something goes wrong. But I figured that's a good way to drill it into your brain, to have tried that and get flustered by a bit and then see why that happened. Failure happens when we have n equations. We've only been dealing with 2 equations so far, but in general with n equations, if we do not get n pivots. So do not get n pivots. Remember that to be a pivot, it cannot be 0. So that's what we mean by not getting n pivots. We'd end up with some number on the diagonal that ends up being 0 at some point, and that would be an indicator of failure. And we've also seen that when we do have failure, when we end up with a 0 pivot, we can have 2 possible cases. We end up with 0 is equal to something that's non-zero. So if you remember, we ended up, for this first one, it was 0y is equal to 8, I think was what that ended up being. In that case, there's no y that we can pick that when multiplied by 0 gives us 8. So that's what I mean by 0 on the left side is equal to non-zero on the right side. And so that means there's no solution for that. And then we ended up with, for the second one, 0y is equal to 0. So there we had 0 is equal to 0, and that totally eliminates that equation. And so then we ended up with infinitely many solutions. So these are 2 important cases. You now have a way of identifying when they happen. And the key is none of the pivots can be 0. Now, we may end up having to exchange the order of our equations to avoid some of these issues. If we do, when we have n equations, when we do an elimination in our very first elimination step, we may end up eliminating more than just one variable in that first step. If that's the case, then all we really need to do is reorder the order of the equations, and we'll see with an example how we do that. So let's move on to 3 equations. So we've got x, y, and z. We've got these 3 equations. So here's our steps. Step number 1, elimination. Step number 2, back substitution. So let's start with step 1. Now, this elimination we'll have to do multiple times because we need to first eliminate these values here. We need to eliminate these x terms. Then we'll need to eliminate this term as well. And if we've eliminated all of those, then we get something that's upper triangular. And that'll be something that we can solve with back substitution. We would solve this first one. There will be different coefficients, obviously. That'll give us z, which we can plug into the second one, which we can solve for y. We can take that resulting y and z and plug it into the top one to get x. So the idea is just keep doing elimination, moving towards a upper triangular form, and then solve the one last equation that should have one variable and then back substitute to get everything else. So in this case, let me clear off some of this ink here so we can see this a little bit better. So we look at our first equation. We find our first non-zero coefficient is 2, and so that's our first pivot. The coefficient corresponding to that in the next row down is the thing that we will cancel. So we're trying to cancel 4. So our multiplier will be 4 divided by 2, which is 2. So we want to take as our multiplier 4 over 2 is equal to 2. So we're going to multiply this top equation here by 2. And so when we do that, we get our multiplier is equal to 2. Subtract 2 times equation 1 from equation 2. And when we do that, this equation is converted into this form. So we now have y plus z is equal to 4. And so that's the result of that first elimination. Now, we look down below and we still have something down here that's in x. So remember, we need to get rid of that. There's only going to be one equation at the top that will have an x value in it. And so, so we need to eliminate that. So our pivot is still 2, because the pivot is the equation that we're using to do the elimination. And our coefficient is minus 2. So minus 2 divided by the coefficient divided by the pivot is minus 2 divided by 2 is minus 1. So we're going to subtract minus 1 times equation 1 from equation 3. And so subtract minus 1 times, that's just another way of saying add. So we can think of it that way. And so after we do that, we end up with the third equation being reduced to this. And so there's our form. Still not upper triangular yet. But we've got, that's fine. We've got this. This is fine because the 2 and the 1 are on the diagonal. But this is not right yet. We need to get rid of that y. It's below the diagonal. So what we need to do is use our new second equation. So we're going to use this new second equation to eliminate this y in our new third equation. So we found 2 pivots. We've eliminated x in equations 2 and 3. We've reached a 2 by 2 system, and we know how to solve that part of it. So if we go through the steps, our pivot is 1, our coefficient is 1, so our multiplier is 1 divided by 1. Do that step, and this last equation gets converted into something that looks like that. And so there is our result. And that is upper diagonal, or I'm sorry, upper triangular. So there's our diagonal, and everything lies above it. So we've transformed from an A that looks like that into a U that looks like that. Now the other thing that's happened is the B is transformed as well. We started with 2, 8, and 10. We now have C, which is 2, 4, and 8. So our claim is that this is a new system of equations that has the same solution as the original. So UX is equal to C has the same solution as AX equal to B. And that indeed is true. And we can see the upper triangular form of this. And notice that along the diagonal of our matrix U, or equivalently along the diagonal of the equations, those are the things that we will call the pivots. So we've got 2, 1, and 4 are the pivots for this system. And so we look at this, we eliminate to something that's upper triangular, and to visualize what this looks like, let's take each of these equations and think about them in 3 dimensions. So I've got a 3-dimensional set of axes here, x, y, and z. And so let's start at the bottom here. Let's look at our 4z is equal to y. We know that that solves to z is equal to 2. And that's this plane here. And you can see that it's maybe a little hard to visualize it, but it doesn't change with x. So for any x value, that plane isn't tilted with respect to x. And likewise, it's not tilted with respect to y either. So this plane here is literally parallel to to the ground, so to speak. So that's kind of key. That's the equivalent of saying that in our 2-dimensional example that we created a horizontal line. Well, now we've created a horizontal plane over the xy plane. So let's look at our next. So that if we solve that, that gives us z equal to 2. Let's look at the next equation. Y plus z is equal to 4. That's this plane right here. So it comes down like this, goes across. We can see there that that also has no dependence on x. You pick any x value, as you change to different x values, we don't see the plane sloped with respect to x at all. That's what it means for this equation to not depend on x. And so now we just take our z is equal to 2, so we plug z equal to 2, that's this plane intersecting this other plane, which is unchanging with x, and they will intersect at a line that it doesn't change with x, nor change with z. It'll only change with y. And so that's the solution of those 2 equations. And when we look at that, it'll give us a solution of y is equal to 2. And then finally, this last plane, which is this one, we look to see where does it intersect the line set by those 2 equations, and that's the final solution. So that gives us minus 1, 2, 2 as our solution to this system. Now, we've not yet gotten into the MATLAB part of this course, but I am giving you some of the code here. We'll circle back and revisit this stuff. But all the stuff that's in black here, so this line, and so forth, you can just type right into MATLAB, and it will create the required results to plot those things. And when we get into studying MATLAB, we'll come back and study these particular commands. The lines that are green that start with percent signs, whether they are an entire line or come after a command that is not green, those are just comments, so you can ignore those. So this command linspace is just creating a range of x values and a range of y values. And then we do this command called mesh grid, and we'll talk about that later as well. And then we evaluate the z, so we have to solve the equations for z is equal to a function of x and y. So very similar to what we did for the 2-dimensional case where we solved y is equal to mx plus b. Here we're doing the same kind of thing, except it's z is equal to some coefficient times x plus some coefficient times y plus some constant. And then we can do these plots here, which will plot all 3 of those planes. Again, just type this in if you want to see how it works and get a little experience typing things into MATLAB, but we'll come back and revisit this stuff. So in general, we've got n equations in n unknowns, and we've got a lot of stuff that we need to cancel. And so basically we're going to use the number that's here. So I'm using x's here not as x, but as some unknown thing. I suppose I should have used something else there, but I'm going to have some number there, and I'll use that to cancel all of these, every single number below that. Then I look at the second column, or I'm sorry, second row, and I should have a number that's in the second position in the second row, and that will be used to zero out everything below that, and so on and so on and so on. And so that's kind of how we do this progressively from the left to the right, canceling all the stuff below whatever's on the diagonal. And when we're all done, we have a matrix that will be upper triangular, and we'll call that matrix U. And we'll have a new set of B values over here from what we started off with. And so if you end up with a 0 as a pivot, so at any point along here, if you end up with a 0 as a pivot, it's something that you have to be concerned about. And we'll see in just, it is possible to, we'll see in just a minute that it's possible sometimes to reorder the equations and recover from a 0 pivot, but sometimes it's not possible to do that. And so if you end up with something where you end up with 0 pivots even after reordering the equations, then you're going to end up either having no solution whatsoever or infinite solutions. So let's take a look at this, these two problems, and I'm encouraging you to try them yourself to see how they work. So pause the video, give them a shot, and then come back and see what I've got to say. Okay, so hopefully you paused the video and you've come back. Let's take a look at problem number 1. So again, I've played a trick on you here. I've given you something that is not a complete failure like you just learned how to deal with, but is just a temporary failure. So let's take a look at what happens here. So there's our original equations, and we say, okay, here's our pivot of 1. We're trying to cancel the thing that's here, so the coefficient is 1. So our multiplier will be 1 over 1. So we're going to just take equation 1 times equation 1 and subtract it from equation 2. And when we do that, we get something that looks like that. And when we do that, notice that, well, we've also canceled this term, right? And we can see why that is, right? Because we have x and x, and we have y and y. Whatever I multiply up here to cancel x is also going to be multiplied by y, and since it's canceling here, it will also cancel here. So there's no way for me to use equation 1 to cancel in equation 2 without always eliminating both x and y. And so suddenly we get to this scenario and we go, uh-oh, I've got a 0 pivot. But if we just look down below, we see, oh, well, that equation does not have a 0 pivot. And so I can actually move that up into the second position. I can interchange the order of these. So there's what I have after my first elimination step. And I just exchanged the second and third equations, and I get something that looks like that. And so now, at that point, I don't have to do any other elimination because, well, I've already eliminated the y in this second equation, which now ends up being the third equation down here. And so everything is good. I've got non-zero pivots on the diagonal. I've got an upper triangular form. I'm good to go. Now we can solve the last equation of this new set for z, back substitute into the second equation to solve for y, back substitute that y and z value into the first equation and solve for x, and I'm done. So here are the steps, and we've got those pivots, and we do back substitution, and we get our solution as z equal to 1, y equal to 2, x equal to 4. So here's problem number 2. All right, so that illustrated a temporary failure and how exchanging the order of equations can fix that temporary failure. But this one has a real failure in it. So just writing the equations, we see that we have pivot of 1, coefficient of 1, so our multiplier is 1. So subtract equation 1 from equation 2, and we also add equation 1 to equation 3, so that will cancel this. So we're basically doing both cancellations in this one line here, and we get something that looks like that. And suddenly we see that not only have we gotten rid of both x's, but we've gotten rid of both y's. And so there's no pivot in column 2. And if we further tried to eliminate a z from one of these, we're going to end up getting a 0z is equal to y. And so there is no solution to this. So these are 3 planes that don't meet, and so there's no solution. Well, they don't meet in any one point, so there's no solution in this case. So in this set of notes, we looked at a systematic way to do elimination. You have to identify pivots, figure out what your multipliers are, eliminate the variables, eliminate all the way down through all of your equations. If you need to exchange the order of equations to deal with 0 pivots, if that's an option, you certainly need to do that. But there are times when you cannot avoid the failures, and when you do have a real failure, you can end up either having no solution whatsoever or infinitely many solutions. And so you need to be able to identify when those situations occur. Okay, we'll see you in the next set of notes.